All right, well, I'm ready now. So here we are. We got our physics test in 2 days, and it's on unit 4, which is just momentum, impulse, all that good stuff. So I'm going to start, and like usual, I will be looking at the chat for any questions or whatever. If you need any clarification or anything, let me know. Also, I've got my phone, so I will look for if you want to use the Remind app instead. That way, you know, whatever you're comfortable with and whatever you need. So let's begin. All right, so there's 2 units. There's two parts to this unit. It's all about momentum and impulse. And the first part is just basically what is momentum and impulse. So we're gonna start with this question: why does the egg break when it hits the wall, but not when it hits the sheet? So we threw a while you're thinking about it. Just to remind you, we threw a water balloon instead of an egg at a sheet, and no matter how hard it was thrown, it never broke against the sheet. Now, it didn't break every time. It took maybe a couple tries when it hit the wall to break, but yeah. So why does it break when it hits the wall but not the sheet? Like, what's the difference between the two? If this was a multiple choice question, well, it is. What would you say? So we'll just take a second. All right, we got an A. Anybody else agree? So I know there's an 18-second delay, so I'm going to have awkward pauses every now and then as I wait for replies, because I want to make sure we get a little bit of replies. Uh-oh, whoop, come back. All right, I'd like to drop these. Nope, that ain't it. There we go. All right. CC, all right. Interesting. All right, the answer. So, yeah, the answer is C. All right, because you got to watch out for little words like absorb, because what does absorb mean? Now, it's not wrong per se, but it's not really explaining what's going on, and so that's the key. That's the thing you got to look out for. Okay, is it explaining? What does it mean to absorb? All right, so all these. The hard, well, naturally breaks are hard, I guess so. It's not. That's. I'm going to change too much. So D is absolutely incorrect. This is just not a thing. That's not true. The other ones maybe you could argue are true, but the key thing here is the time. So if you just remember, Ft, the force times time, is going to be equal to the change in velocity times the mass. And the mass of the egg is going to be whatever it is regardless, or the water balloon, whatever. And the fact is that it's going to stop. Somebody threw it, and it's going to stop when it hits the wall, or it's going to stop when it hits the sheet. And so this right side of the equation is pretty much unchangeable. So the only thing that you can change really is either force or time. And so when it hits the sheet, like in this video down here, this GIF, what it does is it increases the time to slow it down. It increases the time for it to stop. And when it hits the wall, basically it's a very short amount of time. And so if you have these two numbers here have to multiply together to equal these numbers over here. So some combination of force and time is required to stop the ball or stop the egg. And so if you have, bottom line, more force means less time, or less time means more force. More time means less force. All right? Very important. That was the whole egg dropping project was all about that. Car crash safety is all about that. You know, why is there why are there airbags in car seats or in car windshield? What are things called? Drivers. I still can't think of the name of it. Holy cow! Steering wheels. Why are there airbags in steering wheels? It's so that if you are in an accident that you can't avoid, you come to a sudden stop. It's that your body doesn't come to a sudden stop. It's sort of slowed to a stop. You get the same effect if somebody slams on the brakes in a car versus if they slowly come to a stop. Okay, if they take more time to stop, you're going to feel less force, and vice versa. Okay, so next question. We got another one. What has more momentum, an apple thrown at 10 meters per second or a bowling ball thrown at 10 meters per second? So just think about it. Put your answer in, and we'll see what we got. All right, Ender Dragon, you can redeem yourself. So, man, all right. D, S, A, all right. D, all right. D. Oh, Ender Dragon's sure this time. All right. We're gonna go with, okay, so this is true. Not A is true. Actually, A is not correct. Or it doesn't actually explain why. Okay, so why does it have more momentum? I mean, this is true again, but it doesn't really explain it. So I'm glad you chose that one for that reason, because you got to watch out for it. It's sort of like the last one. Technically, it is true, but it's not the best answer. Yeah, I know. It's okay. The apple does not have more mass, so that is absolutely not true. So I'm glad nobody chose that. The bowling ball is not going faster because it literally is going the same speed as the apple. So the answer is D. That's just what it is. It does absolutely have to do with this equation. So momentum is P, and if they're moving at the same velocity, but one of them has a bigger mass, well, then you're going to have a bigger momentum. So that's just how it is. All right, so just take your time. Yep, it's okay. Which bear is best? Oh, wait. Oh, hang on. I'm not sure how that got in there. Next one. What are the variables to represent the following? Well, dang it, Miriam. All right. So, what? Dang it. All right. Impulse. What would that be? Well, that would be, you know what? If I wait 15 or 18 seconds for every single one, this is going to take a while here. And so I'm just going to kind of review, and you can hopefully like get this in your head before I do. So impulse is I. I mean, this shouldn't even be like a challenge for you right now. Force, well, I mean, that's a capital F, okay? Time is a lowercase t. Mass, all right. And there's a delay again. You guys are good. All right, velocity. So once again, hopefully you're getting this before I'm going to go. So I'm just pause here. What's momentum? Don't overthink this one. All right, lowercase p is momentum. Change in velocity. We'll see this a lot. So what's change in? Change is going to be that Greek letter delta. Good. And yep. And change in momentum is that triangle P. So that delta, good, yes, lowercase p. It doesn't technically matter, but later on in another class or something, another situation, you might run into a capital P. So we just want to be like, I don't know, respectful of what, yeah, it's lowercase p. So just make sure that these are, like second nature to you. Okay, so go through and make sure you get all that, all right? So, next question. You throw a ball with 400 newtons of force for 0.2 seconds. How much impulse did you apply? How much momentum did it gain? Well, first question is what is the impulse it gained? And the question is how much momentum did it gain? So I guess that's delta P. That's the change in momentum. How much does the momentum change? So just think about it a second. And if anything, how would you find that out? Let me get a drink of water. Well, pretty good. All right, so impulse is just equal to force times time. That's right. Yes, but where's the problem is you're right. But what is N? N is force. You are correct, Miriam. It is you multiply mass and velocity, and that will help you, especially for the momentum part. But we don't have that. So we have 0.2. This is a lot harder when I don't look at it. This is time. That's all we're given. And so the impulse is force times time, which you can do. So that's 400 times the 0.2 seconds. and that does indeed give you the 80. And the units, if you remember, are Newton seconds. So we did that lab. When you found the area of, like you had that little dip and you had to find the area under the line, or this is hard to draw, sorry. You had to find that area, and that's a graph. The area was given to you in Newton seconds, and so we were finding the impulse even back then. So this is the impulse, 80. So you got that right. Now, for change in momentum, absolutely. You can just do mass times change in holy cow, I screwed that up. Come back. There it is. Let's just start that over. All right, you can do mass times change in velocity. Pushing wheel. Come back. All right, mass times change in velocity. So you'd be right there. But we don't have mass and velocity. So the other way to get this is change in momentum is equal to impulse. All right, that's on the equation sheet. There's that whole string of things that are equal to each other. Just pick the two that apply, and in this case, it is equal to impulse. And so we already know that impulse is 80. Now it's not going to be Newton seconds. It doesn't really matter because it's multiple choice. But I mean, technically, it's kilogram meters per second. And so that's how much. So bottom line is, the momentum it gains is equal to the impulse. Okay, so that's what this equation is telling you. However much impulse you apply to it, that's how much momentum it's going to get. All right, wonderful. I love it. You guys are all answering, so keep that up. It's going to come in handy someday soon. All right, a 15 kilogram ball slows down from 10 meters per second to 5 meters per second. How much did its momentum change? So, how would you do this one? I know somebody who knows it because they just replied. Copy paste it. You're correct. Oh, interesting answer. That is true. How much does momentum? Oh, hey, you are technically correct. It would lose half its momentum because it lost half its speed. But how much? So I didn't catch that. But how much did it lose? All right. So you do know, and you just said it because you multiply mass times velocity. All right, or in this case, mass times change in velocity. So the mass. I actually don't know if that's correct. Ha! Let's find out. So the mass is 15 kilograms. Oh boy. And the change, okay. Let's find out. Because I don't know. 75 seems awfully high. So change in velocity is, and you take the, let's see, it started out, well, here's the initial velocity. Here's the final velocity. So a little debate here. Let me just get to this, and I'll talk about this in a second. So 5 meters per second minus 10 meters per second, and so 15. That's a minus sign right there, in case you couldn't tell. So that is basically 5 minus 10. So it's going to be 15 times negative 5. So it is 75, isn't it? 15 times 5. Why don't I know this right off the top of my head? 5, 10, 50, and then a few more. So yeah, 75 is good. So negative 75. So you're all wrong. Well, no, you're not. Kilograms meters per second. So that's how you find it. You find the change in velocity. Now, did you have to do this part here? I mean, no, yeah, you had to. I mean, you could look at this and be like, well, it slowed down from 10 to 5, so it just changed 5, right? It went down 5. That's basically, you can just get that. You could get the negative 5 just by thinking it through. So even if you don't remember this particular equation thingy right here, just think it through. How much did the velocity change? Okay, so the velocity changed by 5, and so we can multiply it by that, and that's how you do it. All right. Realizing there is the 18-second delay. If you have any questions, please type it in. Plus the delay it takes you to type it. That's okay. I will go back and answer it, okay? Because I want to keep moving, but I also realize you might have questions. So please ask, all right? And we're going to have time. I'll make time for the review guide if you have specific questions about those, but we can answer those in class tomorrow. So This is, yeah, you guys are doing good. So change in momentum is mass, which doesn't change, times change in, well, okay. Ooh, good question. Is it south? It could be. It could be south. But the point is, we never defined negative to mean south. We just now see negative is a mathematical thing, and we in physics have taken this mathematical thing and we have twisted it and used it for our own good and our own use. So sometimes we say negative means south, sometimes we say negative means west, sometimes it just means down. In this case, it means it lost it. So it depends on the context of the question. So in this context, in this question, in the context of this question, the negative just means that it lost it. Now, you wouldn't be necessarily incorrect there, but you had to be predefining like you'd basically had to be saying the ball is heading to the north. And if the ball is heading to the north, then yes, Noel, you'd be absolutely correct. Okay, but you see what I mean? But it depends on the question and it's however we use it. So that is a phenomenal question. All right, thank you. All right, if you have any more, I'll go back. Just keep asking. All right, so next one. I feel like we just saw this one. We did. All right, well, hey, we just got through one. Yeah, no, yeah, for sure. That's a good question. I think this is the same question. Yeah, there's no difference here. All right, so I slipped up there. We had a duplicate. That's what I get for making it quickly. All right, so an acceleration occurs every time there's an impulse. True or false? Or something else? True or false? A or B? Mia, you're funny. Exactly. Oh, okay. Wait. Well, you said F. That's good. True, maybe. All right. All right. Good call. All right. That's why I asked this question, right? I asked this question because, all right. And so, why would I ask that? Well, okay. Don't forget, this is the end of the unit, end of the semester, and so there's gonna be always a little bit of like old stuff in there. So if you think about it, do you remember F equals ma? Or actually, this goes back. This is Newton's second law. So Newton's second. Holy cow! What is that? That's not a letter. That's not an abomination. So Newton's second law. And if you don't remember, Newton's second law is if there's a force, a net force, there will be an acceleration in the direction of that net force. So if there's a net force, there will be an acceleration in the direction of that net force. So what's an impulse? Impulse is equal to force times time. So because of that force, the answer is true. Okay. I know it says every time, and we're trained. Whenever you see the word every time or always in a test question, it's wrong. True, it's false, but not in this case. Okay. But because of, so Alex got it right. Because of Newton's second law, every time there's a force, a net force, you're going to have an acceleration. All right. So if you see the word acceleration on a test or a question, don't freak out. All right. If there's a force, there's an acceleration. If there's a net force, there's an acceleration. So, all right, cool. This is why we're doing this, right? So, all right. There's a lot to know. This isn't going anywhere, too. I mean, you don't want to watch it again, but maybe you're taking notes or something. I don't know. All right. So, which one is going to experience a greater impulse? Car that's pushed with 2,000 newtons of force for 10 seconds, or a truck pushed with 5,000 newtons of force, 4 seconds. I do need a soundboard. I need like the Jeopardy sound or something. Maybe next time. But maybe that would be annoying. All right. I've counted to roughly 18. And so, well, let's find out. It wants impulse, right? Impulse is force times time. So if we take the force times the time for each of these things, take the force times the time. So 2,000 times 10 is 20,000. Let's find out. And 5,000, that's for the car, times 4 is also equal to 20,000. So yeah, do the math. Don't do the math, all right? That's what physics is all about, is taking situations where it's that's all right. Yeah, you're not dumb. We're studying, right? So don't worry about it. That's how it is. So that's what I'm saying. Like, don't necessarily go off your gut instinct on some of this stuff. That's what physics is all about. It's taking situations where it's like, oh, clearly it's going to be this thing. It's like, well, hang on. Let's look at the numbers. So that's what's going on here. So since we get 20,000 for each, yeah, they're the same. All right. So just check out the numbers. Don't necessarily go by, oh, it's a big old truck or it's a little old car. All right. You're gonna have time. Take your time and go with the numbers. All right. Don't feel dumb about it. That's why we're doing this. So what? I don't know why I'm getting all these repeats, but so next question. At one stoplight, the driver takes 10 seconds to accelerate to 40 miles per hour. At the next stoplight, the driver takes only 2 seconds to accelerate to 40 miles an hour. So how much more force do you think you'll feel at the second light? All right. You're going to feel thrown backwards, but really there is a force of the seat pushing you forward. So how much do you think you're going to feel? It takes 10 seconds versus 2 seconds to accelerate to the same speed. You got some answers, all right. So it takes, in this case, it takes 5 times more time to accelerate. This person the second time accelerated 5 times as fast. So because there's 5 times less time, you're going to feel 5 times as much force. It's proportional. 5 times, I'm saying the word times a lot, so I'm using it in different ways, but 5 times 5 times less time means 5 times more force. All right. It goes along with that whole, if there's more time, there's less force. If there's less time, there's more force. All right. It's that proportionality thing. So that's what's going on here. All right. Got it? 18 seconds later, I'll see if you got it. All right. Cell phone cases. Smart people have one. I do not. But they serve a purpose. Why? What? Besides giving you something to grip, if you drop it, why does it make a difference? Take longer to stop, so there's less force. It slows down so it doesn't hit fast. It increases the time and decreases the impulse. Soft and so it absorbs the impact. Yes, Noel, it is always the case. Force and time will always be proportional like that. All right. Inversely proportional. So as one goes up, the other one's going to go down proportionally. Everybody's saying D. Ooh, except for Alex. Sam, maybe. You guys are awesome because you're falling for my traps every time. Absorbs. Remember we did this in like the first or second question. What does that mean? It is true. It is true. You living on the edge. I know, I do that. Yeah. So D is technically true, but it doesn't explain what absorb means. All right. What does that even mean? And that's what we're getting at. So you guys picking that, don't pick it on the test. If you see a question like that and you see the word absorb, be very wary of choosing that choice. All right. Now, yeah, I know, right? So This, hey man, this is why you're doing it though. Okay. Be careful with letter C, because the point is it does not. The impulse is going to be when your phone hits the floor with a nice fancy case on it, and my phone hits the floor with no case on it. They're both going to experience the same impulse. They're both going to experience the same change in velocity, and so they're both going to experience the same impulse. All right. So this is part of it is not true. This part is true. It does increase the time, but the second part is not true. All right. This part is just kind of nonsense. I made that up. Well, I made all this up. So that kind of leaves us with choice A. It seems like I'm using the smallest words there, and I am, but that's the correct answer. It makes it take longer to stop. It's like when the water balloon or the egg hits the bed sheet. It takes longer to stop, and so there's less force. All right. It's all about that force and time. More time means less force. Whether it's the bed sheet and the egg or the water balloon, whether it's the airbag in a car, instead of hitting the steering wheel and stopping like instantaneously and hitting and damaging your head, whether it's like a pillow and being soft, and so you like just don't feel like hardness when you lay down or whatever, or a cell phone case or whatever. It's all about increasing the time to take less force. So you guys are doing good, yeah. You guys are doing great. I love you. You guys are doing great. This is what it's all about. All right. If you were experts in this, you'd be sitting right here where I am. And I don't even really think of myself as much of an expert. I just know a lot of things. All right. If a small car hits a large truck, all right, that's sort of not a lot to say. So what are we gonna do? So I'm gonna just shut up for a few seconds and let you read these. I always doubt myself, and you should doubt me and yourself. And others. Don't assume they're wrong, but don't assume that they're right either. All right. So, you know what? I think this might have been on the last quiz. I forgot though. It's been a while. All righty. Well, you're awesome. Let me see if you were right. You are correct. We have a winner. We have a winner. All right. So here's the thing. Why? Why? All right. All the questions deal with impulse. So let's really quick talk about what impulse is. Impulse is force times time, right? Mm-hmm. All right. In a collision, when a car hits a truck, the time is going to be the same for both of them. Absolutely. Okay. I mean, they hit, and you can't have a collision without two cars. So as soon as the collision ends for one, the collision ends for both. All right. So time is very clearly going to be the same. I'm going to try not to mess this up. Oop, I messed it up. Oh, crud. What did I just do? It is X. I messed it up. Hey, guys. Let's go back to that. I don't even know what I was trying to do. I'm going to stop. So, point is, the time is going to be the same. And the thing that's also going to be the same, though, is the force. And that goes back to Newton's third law, where for every action force, there's going to be an equal and opposite reaction force. Equal and opposite. It's like when the bug splatters on the windshield from that last test. They're both going to feel the same amount of force. The bug is going to accelerate a lot more, going back to unit, what was that, 3, 2? But point is, they are both the same, okay? Both force and time are going to be the same for both the truck and the car. Okay, that's all I could say about that. Force and time are going to be the same. All right, so C is the only one that's correct. Nice job, Noel. All right, now I can't go to the next slide. Holy cow. There we go. Okay. Type questions in there if you got it. I'm going to move on though. All right, a car is pushed with 500 newtons of force for 5 seconds, causing it to speed up from 5 to 9. Going by this equation right here, what's the mass of the car? How do you even, so we got the formula. Moi, get some water. I think you can do this without much of a calculator. I try to use easy numbers. So while you're working it through, this is your force. This is why scratch paper is going to be useful. So I'll make sure to have some on Friday. This is your time. This right here is going to be your change in velocity. All right. In this case, it speeds up, so it's going to be a positive change. So it's going to be 4 meters per second. Maybe. So force, why am I going to rewrite this again? It's already written up here. So I'm going to go off of this. So force is 500. Well, we've got confirmation. So we're going to, I believe you're right. And so that's your time. And our mass is our question mark. I did not get that. So let's, all right. Oh, yeah, that's okay. Let's see. All right, so 4 meters per second. All right, so 500 times 5, what is that? 2500. And then I'm just going to leave units off for now. Is equal to 4 times m. So if I divide both sides by 4, then 2500 divided by 4, I'm guessing that's 625. It is. All right. So 625 is equal to m. Okay, units and all that, but I'm trying to be brief here. So nice job. Does that make sense? Does that make sense? So all I did, and I'm going to just tell you. So mass, I forgot to identify that. So just go through. What are these numbers? What are these numbers? And this is what I was talking about, like the very first or second or third slide, whatever. It's like, what are all the the letters? Make sure you're good with those. All right. Check out that part on the review guide. I think there's that part. There's some questions. Okay. Good. All right. This was interesting. I tried to find an animated GIF. I said GIF about this, and I couldn't. I thought, well, I'll just record it myself, and I didn't because things happen. I just made this up today. So we have a wall, and we have a blob of slime thrown against the wall, and we have a ball thrown against the wall. And the blob just kind of sticks to the wall, but the ball bounces back. All right. Same mass, thrown at the same speed, 5 meters per second, but the ball bounces back. Man, all right. CCC, we got confirmation, both the same. Interesting. Everybody says C. Wow, I am glad I asked this question. The answer is B. The answer is B. Why? Why do you think? What's the difference between the two? Let's put it this way. What if I asked you which one had the greatest change in momentum? Which one would that be? Well, the slime had a momentum going this way, and it went down to 0. It stopped when it hit the wall, okay, for the slime. the ball, I know, right? That's why I'm asking. That's why I asked this question. The ball, it went down to 0, and then it reversed course. Alex, you are absolutely correct. It reversed course because the wall pushed back on the ball. The ball pushed on the wall. All right. And so it went back up to basically negative P, whatever it had before. Yes. So because the ball did a total like reversal, it didn't just lose its momentum, it gained more momentum. Well, and then more momentum, but I mean, it gained more momentum. It lost some momentum and then it gained it back in the opposite direction. So because it had the biggest momentum change, okay, the ball has the biggest impulse because the wall had to push back harder on the ball. It doesn't necessarily make sense intuitively because it's like, well, they both, like, the wall doesn't push harder, does it? But it does. All right, it does when you think about it this way, and it's because we haven't really had a situation where you would see something like that where you could tell, like, just I don't know how to say it, but like if we were to somehow throw a blob of slime at a bed sheet, you would see, and we held it tight, you would actually see it not go back as far because it's not pushing, like it just takes away, it doesn't push back. So because it pushes back on the ball has a bigger change in momentum. You guys are right. I love it. I'm glad you guys, like, many of you, like, I had the wrong answer first and you thought about it. You're like, oh yeah, because that's what this is all about, right? All right. Think about that one. You could always ask me later. Okay. Alrighty. So we are okay. You know what? That was the first part. I'll come back to that in a minute. We're gonna get on to conservation momentum. It's already been 40 minutes. I don't know how that happened. All right. So we are almost done. There's not quite as many questions for this one because it's pretty straightforward, but a little bit more difficult in some ways. So we got a motion cart moving at 10 meters per second, colliding with and sticking to an identical motion cart that is at rest. How fast do they move after they stick together? Okay, so identical motion carts. Yes, this is from today. Yep. The answer is C. The answer is C. It's definitely not green. Incorrect. So the answer is C. Yeah. That is from your that's yes. Caitlin, I think. Is this you? I think that's you, Caitlin. I don't remember though. Yeah. So Miriam, wait, is this? All right. We'll talk later. So yeah, it's C because they just doubled the mass of the two carts. Why? Because, and I was just about to say that. Why? Because when they collide, the two masses come together, and because the momentum doesn't change. Why is it C and not B? Right, because the momentum doesn't change and the mass just doubled. Well, then that means the velocity has to get divided by 2. That has to, because it has to balance out. Okay, if you double the mass, the momentum doesn't change. Total momentum doesn't change. You just double the mass, then something has to change, and it ends up being the velocity, right? So when you collided the carts, there's definitely a slowdown, and so since they're equal masses, they slow down by half. Okay, so think about this one. A ball is going 10 meters per second. So once again, similar type of situation. Now the ball, this time it bounces off another ball that has twice the mass. Okay, so careful with that. It's got twice the mass. So it's a little ball bouncing off of a big ball. Okay, bink. How fast does the second ball go? Oh, it stops. The second one stops. So ignore the bouncing part. Come here, little. I need not you. There we go. So it does not bounce back. How fast does that second ball go? Not D. Thank you for playing, though. I ran out of choices. I couldn't think of any more. Incorrect. Incorrect. All right. How fast will the second ball go? So once again, this ball stops. Okay, it stops after it hits the ball. And this ball has basically twice the mass of the second ball. So if the little ball, the little tiny ball is hitting the bigger one, is the ball going to go faster, slower, or the same? It's twice the mass. I'm wondering where you're getting A from. Good choices, though. You had the right idea, but you were thinking about it backwards, maybe? So, I mean, a little ball. I can't even read that word. Oh, it stops. A little ball hits a big ball. The big ball is not going to go twice as fast. Why? Because once again, the momentum stays the same. How is it? It's not A. It's not A. So momentum stays the same. So if you, once again, if you double the mass, you're going to have to take 1/2 the velocity. All right. So because it's going to be equal to each other. So if that momentum, the momentum at the beginning, the total momentum stays the same. So the momentum doesn't change, and you just double the mass, then it's going to have half the speed. All right. Not A, it's C. I'm pausing because I feel like there might be a question. All right. Think about it. If you have a question, we come back to it. Couple more. Right. Okay, good. Yes, I almost had my brain broken. Yeah. I think you guys might be good at the grids, at solving like those chart problems, but I fear that by doing that and focusing a lot on that, we may have lost a little bit of the conceptual stuff behind it. And that's often the case with, especially in an honors class. Everybody gets the math, not everybody, but sometimes the honors students can get the math pretty quick because it's just, I follow this formula and I got the answer. But did you understand why you got the answer? And I've been there, I know all about that. So just think this one through, and you'll get it. All right, yeah, I understand. So, all right, so a lot of more numbers here. So a 100 kilogram object loses 10 kilogram meters per second of momentum. Now you don't have to do a chart problem here. You barely have to do much math. Just think it through. Let's talk about this. So you got a 100 kilogram object losing 10 kilogram meters per second of momentum during a collision with a 50 kilogram object that is at rest. So it has half the mass. I don't know if that matters, but let's move on. How fast does that 50 kilogram object move after the collision? If the 100 kilogram object lost 10 kilogram meters per second of momentum. I'll let you think about that a second. There's a lot of numbers floating around, and they're not all necessary. All right. All right, good. You guys are thinking in proportions. Not bad. Let's see if you're right, though. Interesting. All right, we have 4 people answered, but the answer is A. I don't know if you overthought it or underthought it, but let's break it down here. I think I need to point out this is not necessary, okay? Doesn't matter. The important information is this right here, okay? It loses that amount. If it loses this, where does it go? If it loses this, where does it go? Well, then gains 10 kilogram meters per second. Okay. It can't be lost. So the 50 kilogram object has to gain it. And it was at rest. It was at rest. So now it gained 10 kilogram meters per second of momentum. P equals mv. I mean, maybe I'm wrong. I'll admit, maybe I'm doing this wrong, but kilogram meters per second is the mass times the velocity. And so if I want to solve for velocity, I got to divide by 50. And 10 divided by 50. Oh, it's not velocity. Yeah. So 0.2 meters per second is the velocity. Okay. I think I'm going to go out on a limb and say that you might have gotten lost with all the numbers. All right. Not just. I shouldn't say just. That's not really nice. Or not really nice. It's not really helpful, I should say. Yeah, look at what's going on here. All right. It's losing this momentum. The other thing must gain it. So since it gained it, okay. Does this make sense? Yeah, right. Yes, this is not velocity. This is momentum. I finally understand. I think I understand what you said, Alex. So that's momentum. All right. Of momentum. All right. So keep an eye on the units. That'll be very helpful. All right. Good thing is, in a few minutes, you'll be able to rewind this and watch it again. All right. Set a timer for 25 seconds. All right. One per customer. All right. Very good. So I believe this is the last question. Yeah. This is the last slide. All right. You've got a 5 kilogram ball moving at 10 meters per second, and it hits another ball and it stops. Okay. Because of the delay, I'll take it. Yeah. I'll take it. All right. 5 kilogram ball moving at 10 meters per second, and it hits another ball and stops. So in this case, in this GIF, it's the blue. The blue ball is hitting that, what is that, orange ball? Red ball. And the second ball was at rest. It's now moving at 8 meters per second. What is the mass of the second ball? Now, ignoring the fact that they're pool balls and they're probably the same mass, forget that. What is the actual mass of the ball? All right. A, B, C, or D. Hopefully you have eliminated one. I mean, think it through a little bit, okay? It's pretty close to 10, so 8 and 10 are kind of close, so they're going to be kind of similar answers. Now, if you had said 3 different colors, Noel, I might have considered it, but oh well. Anyway, so what's the mass of the second ball? C, perhaps. All right, well, it kind of goes back to that previous question. How much momentum did the first ball have? How much did it lose? And then, because it lost it, how much did the other ball gain? All right, so the mass of the, we'll call it the blue ball, is going to be 5 times 10. So I'm not going to put units because, you know, I'm getting tired. So it had 50 kilogram meters per second of momentum. And so now, this is, I guess, before. We start thinking in terms of before and after. So then after, the red ball now has 50 units of momentum because it stole it from the blue ball. Look at that. Like this, it's just sitting there minding its own business. And there comes the blue ball, and the blue ball just gives it 50 kilogram meters per second of Yeah, so, all right, you're way ahead of me. So once again, if 50 is mass times velocity, and we know that the mass is going to be, what is that? Oh no, we don't know mass. My fault. We know that the mass is going to be, we don't know the mass. You guys are ahead of me. I'm slow here. All right, so I'm going to divide both sides by 8. And so the mass is going to be 6.3 kilograms. All right, I believe that's right. You guys all with me? Yeah. Wait, hang on. If I divide by 50 divided by 8. Now I got to recheck that. Yeah, 6.25. It comes out to 6.25 in the calculator. So I made that trickily close to each other. So you'd have to, if you guessed, you'd have to like, but you see what I mean though? So the red ball took all the momentum. And so I know. So since we know the velocity and we know that the momentum, the red ball took all the momentum, and we just multiply mass times velocity, then that's how we could get that. That's what I did there. All right. And that, yeah, and that's all conservation momentum. The whole idea of conservation momentum is that these are equal to each other, all right, before and after. All right. And all these things kind of relate to that. Excuse me. So, yeah. So conservation momentum. All right. I just thought it was B because the first ball stopped after the second ball had to have the same mass. Yeah, I kind of might have messed you up a little bit because the picture is two billiard balls, but I won't do that in the test. Okay. But wait. Oh no, not necessarily. Not necessarily. That's good thinking though, Sam. Honestly, that's really good thinking. But do the numbers and then we'll see how it goes, just to make sure of that, I guess, because it doesn't always. That's not always the case. Yeah, that's Mr. Farias. He teaches physics at West. He's pretty amazing too. So he knows how to play pool. So watch out. Yeah. All right. Moving on before we start talking too much about pool. All right. One other thing I didn't talk about in here is make sure you can solve conservation momentum's questions. So if I were to, switch to, where's my mouse? Okay. If I were to go like these questions on the review guide, make sure you could do those and you could get the right answer, because I did not talk about these on the review at all. All right. You got to be able to, it's all, this is the mathy stuff where, you might be really good at it, but you might not have really realized what you were doing. So make sure you know all these things and you'll be fine. Okay. But I didn't want to mention that. There's videos linked below on the doobly-doo, and those walk through all three, like elastic, inelastic, and explosions. By the way, make sure you know the difference between those three things, especially inelastic and elastic. To clarify, elastic collisions bounce off each other. Inelastic collisions collide and stick to each other. Okay? And explosions start as one object and they separate into two objects or more. Okay? So, any questions? Any questions? Sorry. Yeah, that's the official internet's term for it, from what I've heard. All right, I'm gonna wait like another minute because somebody might be texting or typing. And I think so. It's just to, okay, I forgot how many multiple choice questions are, but it's a mixture of multiple choice. There's gonna be a paper free response question again, just like before. I think there's 2 questions. Just don't overthink these things. Okay, just remember the equations. Just keep those in mind. Okay. And you are very, very welcome. I hope the extra credit was helpful, along with all the other stuff that we did and we talked about today. So it's always nice to get a little bonus points. So thanks for joining me here, and I do hope it was helpful. De nada. So you guys, I will see you tomorrow. We'll probably do a little review. I might have a Kahoot. I don't know yet, and then the test will be Friday. All right. All right. Wait, are we gonna review? Yes, a little bit, Noel. You read my mind. All right. Very good. Too late. Besides, I don't even know who you are, Ender Dragon. All right. Wait a minute. Now I know who you are. I know who you are. Thanks for the music suggestions. It actually made a big difference. All right. You guys have a good evening, and I'll talk to you tomorrow.